in today's lecture, we are going to discuss the direct shear test, which is chapter 6. If you remember in chapter 5, the last section of chapter 5 was dedicated for the direct shear test. And we said that we are going to discuss it in details in a separate lecture. So the direct shear test was a test that is conducted in the lab to get the shear strength parameter, which is the C and the phi of the soil. But in chapter 5, we did not discuss only the direct shear, we discussed the direct shear, and previously we discussed the triaxial test, which is a very elaborated test with that can simulate all the cases. It is really a very, very good test because it simulates nearly every case in any loading or in any soil structure interaction problem like a foundation or something like this. But it is, because it is very complicated, it is not always used. It is difficult to use it all of the time. Usually we use part of which is the unconfined compression test. This is an easy test, similar to the test that you conduct on concrete samples just to reach failure for this samples. So we usually conduct the unconfined compression test and we conduct the direct shear test. Both are not exactly the same, because the same as the real case, because in the unconfined we don't have, from the name it is unconfined, it means that we don't have anything around the sample, and this is not the case in soil. If you get a sample inside the soil, it will be surrounded by soil from all directions. So this is a hypothetical case. It is not the real life for soil samples. And this test, we have our comments on it, but we will discuss it when we discuss the test now in our lecture for chapter 6. So, direct shear test is an experimental procedure conducted in geotechnical engineering practice and research that aims to determine the shear strength of soil material. Shear strength is defined as the maximum resistance that the material can withstand when subjected to shearing. So, using this test, I will get the maximum that the soil can carry. Generally, direct shear test is considered one of the most common and simple tests. That's why we use it. It is common and simple, and it is in every lab, every place, so we cannot ignore it, even though we know that it is not the best, it's not giving the best results, or there are some comments on the results. And can be performed on undisturbed or remolded samples. Of course, when I tell you I'm going to get undisturbed sample, this is also approximate, because what do I mean by undisturbed sample? Undisturbed sample, it means that a sample that I managed to bring from the site to the lab and it is undisturbed. Undisturbed means that it is intact, similar to its condition on site. Never I can do this, because to carry a sample to extract a sample to get a sample from the soil and to take it to the lab inside a tube and then extract it from a tube and put it outside and then start testing it, I'm disturbing it. But I mean by undisturbed that you can add undisturbed as much as possible. It is not 100% undisturbed and it is not 100% disturbed. It is something in between. Of course, remolded means that it was completely destroyed before coming to the lab. In soil mechanics, The shear strength is evaluated using more column failure criteria. The more column criterion assumes that the shear strength depends on three factors. It depends on the normal effective stress, it depends on the friction, it depends on the cohesion. So it depends on three things. One of them is the normal stress. You remember the photo that I have given you for somebody trying to pull a raft with his sister and his dog on top of it? Maybe. Anyway, imagine that you are trying to pull, you have a car that is on the ground and you want to push it. Or you have maybe something at home, you have a refrigerator and you want to push it from its place. If it is a small refrigerator, you can push it. But if it is very big refrigerator, you will find difficulty in moving it. Why? Because the friction of the heavy material is more than the friction of though they are the same brands, same shapes, same everything. But this, because the load is heavier, so the friction is more. So first, the normal effective stress. So the normal stress on the material increases the strength of the material. Then the friction, which is the phi angle, and the cohesion, which is the C of the soil. These are the two parameters that I want to get from the tests. The first one is the load. I can calculate the load easily. Just calculate the load on any footing. But I want to calculate the C and phi of the soil. Then I need to perform a test. All of these are included by more in a equation. This is the equation of the straight line in more that is tangent to more circuit. We are going to discuss it. Of course, we have discussed this in the previous lecture, but we are going to repeat it now. So tau is equal to C, which is the cohesion, plus sigma n, which is the normal vertical stress, multiplied by tan phi. So I have here phi, I have C, these are the two parameters, and I have sigma n, which is the normal stress. They all give me the shear strength of the soil. This is the normal shape of a curve that I would expect if I conduct the tests, the shear strength test, for two types of soil. This is for sand, cohesionless soil, and this is for clay, cohesive soil. What is the difference between cohesive and cohesionless soil? What is the main difference between sand and clay? Anybody know? It's a very a basic question. No, I mean in terms of parameters. What is the difference? If I tell you that this is very important, because in the exam I may not give you a soil parameter and will just give you the name of the soil. If I tell you I have pure sand, from this word pure sand you understand that C equal to 0, no cohesion. Because by the name, it is cohesionless soil. It means that it does not have any cohesion. So this is the first one. And if I tell you that it is pure clay means phi equal to 0. So this is the main thing. So if I have a sand, it means that I don't have any C. If you remember, C was the intercept that this line makes with the vertical axis. So in this case, for sand, it starts from the origin, from 0, 0. It means that C equal to 0. The opposite for clay. If it is clay, then it means I have a C, and I may have a value of phi, and may have a phi of 0. If I have a value of phi, then this will be an inclined line. If I have a phi of 0, then this line will be parallel to the x-axis. These are the shape of the test, because in some cases you may not get the value of the parameter, and instead of having the value of the parameter, you are given, it is called pure sand or pure clay. Then you have to understand what does this mean.
Pure clay friction zero.
If it is pure clay, then the phi is equal to 0. No phi. It's just C. In this case, this will be the case. But usually, especially in clay, I will have some kind of phi. Maybe it is a very low phi, but I will have phi. But in sand, if I have pure sand, you are sure 100% that the C is equal to 0. But sometimes in the clay, though you have C, but you may have small angles of phi. But in an exam, if I tell you that you have pure clay and I do not give you the value of phi, then you will take it equal to 0 without discussion. This is the shape of the test. The shape of the test is like this. I have a soil specimen. This is the specimen. By the way, do you know what is the difference between sample and specimen? They are both two English words. Usually they are used instead of each other, but there is a difference between both. Sample is the sample that I take, is the bulk sample that I take from the site, or a big sample. But if I take this sample, prepare it to fit into my experiment, then it is a specimen. So, specimen is the tailored part of the sample to fit my testing apparatus. So now, here it is called specimen. I cannot say sample, but I take soil sample from the site. From this soil sample, I will take many specimens to be tested in the equipment. So this is the specimen. This specimen, as we said, that it may include water, and I want this water to dissipate. How can I do this? I should put a porous plate on top of it and a porous plate at the bottom of it. This plate helps that water can penetrate this plate and go outside. So this is important to have this one. And above here, I have something called a loading cap, because we said that here we have C and we have phi and we have the normal stress. So in this test, I should be able to apply a normal force to induce normal stress on the sample. So this loading cap is where I will put my normal force to apply it on the sample. The blow, this is, they call it a gripper disc or anything. It is a way of fixation for the bottom part, because this sample or this specimen is inside a big tube, but this big tube is split into two halves. The lower half is fixed and the upper half is movable, and that's how we are going to shear our sample. To shear the sample or to shear the specimen, the bottom tube will be fixed and the upper tube will be pushed, but it will be pushed by a controlled device. I will push it with a certain horizontal stress, and while pushing it, I record what happened to the sample, how it moves. So this is the shape of the illustration for this. And here, this is called a clipping screw. This clipping screw, when I put it, it connects both parts of the sample. If I remove it, then the upper part will be free to move. So it's just for fixation. This screw is just to fix the upper part with the lower part. If I remove it, then the upper part will be free to move, but the lower part is fixed to this gripper disc, which is fixed to the ground, so I cannot move it. This is what we've just said. Here it says that the shear box may be circular or may be square. I can use the sampler itself. This one, it may be square. Usually it is 6 by 6, or in some cases it may be circular. Both are okay. It's not a problem. But I have to know it in my calculations. This is the shape of the test. The shear box is then placed in a shearing device. Initially, a direct normal pressure. This is the first thing. First thing, I have to apply a normal pressure on top. This. So I can do this test many times using the same type of soil, but each time I change the value of the normal stress. What do you expect if I increase the normal stress? Would the soil be stronger or weaker? Anybody can think? If I increase the normal stress on top of my sample. Stronger, yes. Yes. Why? Because when I increase the confining pressure or the pressure on top, then any other pressure acting on the soil should be more to overcome the effect of the normal stress that I have added. So it means that I can conduct the test first with very small normal stress. I will get a value for C and phi. No, not value for C and phi. I will get value for the shearing stress that will the failure stress. If I increase the normal stress, then next time the failure stress in shear will be higher than the first one. But of course, C and phi, these are soil parameters. They depend on the soil material itself. If I have sand, then I will have sand and C and phi with a specific number. It will not change. But this test, I'm doing it more than one time just to get the value of C and phi. This is what we've just said. Before the shearing stage begins, one metallic plate is slightly raised to ensure that the just something as in the procedure that I should ensure that the upper part and the lower part can move freely, because suppose there is something preventing them from moving, it will give you wrong results. This is something related to the procedure. This one. Afterwards, this is the test. I prefer just to say it directly here. When I put the normal force on the sample, this normal force will be applied on the sample. I will just remove these clamping screws to ensure that the upper part can move. Then I start pushing the sample from the top. When I push the sample from the top, the sample will start to move. There will be something in the machine to record the horizontal stress that I'm applying and the amount of deformation or the movement that is happening. So I will have two things. I will have a normal force affecting this section. This is the normal force affecting this section. And I will have a horizontal force from this direction, and it will be also shearing the same section, because I'm forcing the section to move the top part to move, leaving the upper part. In this case, my soil will be sheared on this line. So I continue with the test till I reach failure. When I push, some deformation will happen, and this deformation will increase till suddenly the deformation increases sharply. It means that this is the failure stress affecting my sample. Once I reach this, then the test stops, and I can repeat this test again with a different specimen, but in this case I will increase the normal force, and so on. Each time I repeat the test, I will get a different load for the shearing value, that the value at ultimate that corresponds to the normal force that you are applying. Usually we repeat it 3 times to use to draw the line. I will just skip this now and then return back to it, but I want to show you how we this is how we do the test. Suppose I put my first horizontal load, so this will be the normal stress, and then I conduct my tests, and I will get a stress in the horizontal direction that is corresponding to failure. So I really got this point, which is at a normal stress, say, of 100, I got a shearing stress of 98. This is the first point. I repeat the experiment again. I increase the normal force. Instead of 100, it is 200. In this case, I get another value for the shearing stress at failure, and so on. 3-4 times, the minimum is 3 times, and so I will get these 4 points, or 3 points if I repeat it 3 times. Usually there are some errors. We don't get the points, all of them on one straight line. There may be some variations. I don't know if I have here. Yes, this is the normal shape that we would get. I would get a point here, another point there, another point there. So usually I draw the line that best fits the 3 points I have. So this is the line that I will draw. If I draw this line, it will cut the y-axis in a point. This is the value here, is the C value of the soil. So this directly will give me the value of C, and the phi is the angle of the slope of this line, so I can get C and phi. So based on the results of these tests, if I repeat it 3 or 4 times, I can draw this line. I will just extend this line till I meet the y-axis. The intercept here will be the C, and the angle of inclination will be the phi. Now this is an important part of the lecture. It says what are the errors in this shear box testing. These are very important. Common errors that occur during direct shear testing include disturbing the sample before the test, not allowing it to fully consolidate, or selecting a shearing rate that is too high. If you remember, we said that the sample, of course, we said that transferring the sample from the site to the lab will induce some disturbance for the sample. So this is the first error, the error due to the disturbance of the sample. Not allowing the sample to fully consolidate. You remember that we said that this is the sample, here is a porous plate and here is a porous plate, and the sample is full of water. When I put the sample and I put the vertical load, I should leave the sample an adequate time so that all the water inside the sample would leave the sample. Otherwise, I will be performing the test on a sample that includes water under pressure, poor water pressure. In this case, I will get wrong results. I will get less results than the expected, because the shearing strength of water is 0. Water has no shearing strength. So if I am letting the water to carry part of the vertical load, then when it comes to the shearing force, water will not carry anything. So I'm just putting the sample in a condition that does not resemble the real condition. So this is the first thing, is that when I put the normal force, I should allow the water to come from the sample before putting the horizontal load. Suppose when I put the horizontal load, I pushed it very quickly. What will happen? At the beginning, I left the sample an adequate time so that water left the required water to leave the sample, left the sample. But when I put the load on the movable part of the specimen, I sheared it very quickly. It means that I did not give it adequate time so that when I push, water dissipate. I just pushed it very quickly. In this case, I will not have the effect of consolidation also here, and I will get wrong results. So this is the third thing. These are the common errors. We said that the first is the disturbance. The second is not allowing the fully consolidation at the start of the sample, or shearing rate that is too high. If the shearing rate is too high, then I won't have, you see here, you have consolidation in two places. Consolidation when you put your vertical load, you need consolidation. And while shearing the test, you need another type of consolidation, because water needs to leave the sample. If I push it very quickly, water will not leave the sample and I will get wrong result. So these are very important, but these I can take it into consideration. How can I take it into consideration? Try not to disturb the sample while moving it from one place to the other. Give it time to consolidate at the start of the test. Use a very low shearing rate so that you would undervalue these errors. So these errors are there, but I can minimize them as much as possible. Disturbance usually affects the sample structure and reduces its strength. Therefore, the results of the tests are not representative of the actual soil behavior. We said that. Similar to failure, to failure of the sample of the consolidation process, a longer shearing rate. This is describing what we said. I need consolidation in two places. When I apply the load at the beginning, I need consolidation, and when I start shearing the sample, I need a slow rate to have to give the sample time to consolidate. Last thing, and this is very, very important thing, the specimen is forced to fail on a predetermined horizontal plane, not the critical plane. Look at this. I'm pushing the sample from the top. When I push the sample from the top, the sample will be sheared on this plane. Is this the minimum or the critical plane? If you remember, in this test, when I push the sample in this test, or even in the confined test, the normal test, which is this one, if I just push the sample from the top, what is the expected shape of the plane? The expected shape of the failure plane would be an inclined plane like this. It means that the failure plane is an inclined plane, not a horizontal plane. So in this test, you are telling me that you want to shear the sample at this location. It means that you are getting higher values for C and phi because I'm not shearing the sample at the location where it is or it should fail. I am shearing it at a stronger plane. So this is a very, very important, this one is a very important factor in giving wrong results or not accurate results in the shear box testing. Testing procedure, it is just written here, but I won't concentrate on it now because you are going to do it when you are in the sample. You weigh the sample at the beginning, you measure the height, the diameter. This is all the testing procedure. You can open it with you when you go to the lab just to follow these procedure exactly what to put the sample, put the porous plate, put the screws and so on. These are the test procedure. We are not going to discuss them now, but here they tell you null the shear force, null the initial dial gauge. Of course, all your gauges should read zero, exactly zero, because if it has a reading at the beginning, it means that you are getting wrong readings. So these are just the procedure how you do this. This you are going to see in the lab step by step. This is a definition of what is the normal stress and what is the shear stress. The normal stress is the vertical force divided by the area that will be sheared, and the shear stress is the horizontal force that you are applying, also divided by the same area, because in this test you are forcing the sample to be sheared at a specific plane. So you know exactly what is the dimensions of this plane. The dimension of the area that will be affected by the normal force is exactly the same as the area that will be affected by the horizontal force. This is in this test specifically, but in the other test, this test, no. What is the area of the test that will be sheared? It will be this inclined plane. But what is the area for the vertical stress? It is a horizontal plane. So in this test only, it is a special case that we are going to use the area of the sampler as a whole. Now this is the test. We performed the test. Here we perform it 4 times. You can perform it 3 times, and then you are going to draw this line. As I said, you extend the line to get the C, and you measure the inclination to get the phi. This is something that would tell you what is the difference of the behavior of a dense sand or a dense material and a loose material. In a dense material, the relation between the shear strength and the shear strain, you will always reach a very high level because in case of dense material, and then once you start to reach the failure, this dense material start to break till it reaches this shape. If you have a loose material, then it is not dense, it will fail directly, but they both will end up having the same line, because this location depends on the material of the soil, if it is sand, clay or whatever, but this shape depends on the degree of compaction. So you have, starting from here, you depend on the material of the soil, but here and there these are depending on the degree of compactness. If you have a dense material, then you will move like this. If you have a loose material, then they are going to move on this line. This is the direct shear test. This is يعني before that we were just saying examples. Here is exact shape. This is how we can conduct the test, drained or undrained. I can I can fill the area around the sample with water so that I ensure that there is water around the sample, or I may not put water and leave it without water depending on the type of test that I want to conduct. Once as I said, this we have seen before, I get the points, which are the 3 points. I get the best fitting for the line that can pass through these 3 points with the minimum error, and then I can measure the intercept and it will be equal to C, and I can measure the inclination and it will be equal to phi. This ends up our lecture, but I want to show you some pictures for this test, or videos. This what I want to show you. This is your test. This is the equipment that you have in the lab. This is how it looks like. This is the sampler where it is here. It is squared, and it consists of 2 parts. The lower part is fixed. The higher part is movable. I will just go through the video very quickly to see how we conduct this test. I will just this how it is working. I will just a moment. Property, not this one. Okay. Here he's putting the sample, and he's putting the porous plate on top of the sample. This is how he's putting the porous plate on top of the sample, and this is the cap on top where I put the vertical load on my sample. He's going to put this. By the way, these are the 2 screws that we have seen in the before to connect the upper and the lower parts. And this is the equipment where we connect our. This is an automatic equipment. Instead of measuring everything by ourselves, this is computerized way to measure everything. So we just connect everything to this equipment, and so on. This is how to start. Then we start our test, but before starting the test, we need to put the vertical load. Let's see how he is going to put the vertical load. This is the part that is going to induce the vertical load. He just free it and then put it on top of this cap. This how he is putting it. Just yes, here he put it, and put it just to touch the cap, and then he start putting weights on this part. If you put weight, then this weight will be the vertical weight. And of course you have many gauges that will be connected to measure the displacement, and these gauges will be also connected the automatic device that will measure everything. We'll continue like this. These are all adjustments to put these. We said that we have to null all of these. Just a moment to open the other one. This is the other one here. Yes. All of these are adjustments. You will see it exactly when you are in the lab. but these are just how we do this, how we get the sample out, how we connect the sample. It's all seen in this video. Here, once we finished everything, we started the test, we go to this screen and monitor the tests. These are the loads that we can put on the vertical, these correspond to the vertical stresses that we are going to add to the test. You put, there is a scale how much we can put, and this load is multiplied by a factor. You will know this when you go to the lab. Then you start the test and you monitor everything in the on your screen. We will not this is enough for the time being. You can now go to the lab and to start your own tests and get your own results. Thank you, and see you next time.